Okay. Thank you, Marco, for reminding me. We saw the definition of absolutely continuous function. F is AC if there is a function integrable such that f of x has this representation. It can be written as f of 0 plus integral from 0 to x g of t dt. And it's more than being continuous. It's a very strong property. And based on the Lebesgue theory of integration, now we know that f prime at point x exists and is equal to g of x almost everywhere. And using this, we define our first Sobolev spaces. I mean, we call it H, such that f defined on 0, 1, and we study the real version of this. The complex version is similar with two properties. First, this G in general, we saw it's in L1, we put more restriction. We assume that f is AC, and moreover, this derivative, which has to be in L1 by definition, now we assume that is in L2, 0, 1. So its square is integrable. And we add two boundary conditions, and we add f of 0 equal f of 1 equal to 0. That's the definition. I will play with these conditions in my second and third example, and even if we have time in the fourth one. And we'll see that it has a huge effect on calculation of K, the kernel. We saw that the H is RKHS. I don't go into detail. And also for the evaluation, f at point x, we have this representation here, and f of 0 is 0. So one of them is integral from 0 to x, g t dt, or f prime t dt, both are correct. And the other one, since f of 1 is also 0, so it's one of them is integral from 0 to x, f prime t dt, and another one is integral from x to 1, f prime t dt, with a minus here, because f of 1 is also equal to 0. And using these two formulas, we saw that f of x is less than or equal to root of x norm of f in h, and also at the same time is less than root of 1 minus x norm of f in h. So both show that the evaluations are continuous, that is considered here, but none of them is optimal. I mean, neither the first one nor this one is optimal. And they just give an upper bound for the norm of EX as an evaluation from H into R. Both show that it's less than or equal to the minimum of root X and root 1 minus X. So what is the norm? What is the norm of EX? And here is we realize the power of RKHS. I recall that we saw after giving the definition that the norm of EX is equal to indeed the norm of KX in H, which is the same as K of XX root square. So we need to find kernel either in the little form or the capital form, they are the same. And then we immediately, by evaluating on the diagonal, we obtain the norm of Ex. So the biggest question is, what is Kx? And for this, we need some tools from distribution theory to find the kernel. From here, it's the new material. So let us start with f of x equal to integral from 0 to x f prime t. No, sorry, not this one. We know this is true, but we start from the fact that f of x is given by f inner product with kx. And by definition, this is the integral from 0 to 1 f of t prime k of x prime t dt. And the integral is well defined. I remind you that in the definition, we assume that f prime and k prime both are in L2, so the product stays in L1. There is no problem. The integral is perfectly well defined. If we know that k has a second derivative, we can do integration by part and write this as f of x or f of t kx prime t from 0 to 1 minus integral from 0 to 1 f of t kx double prime t dt. For momentarily assume that everything is okay, k is smooth, and we can do integration by parts. If we do this based on the assumption, again, on the boundary values, at point t equal to 1 and t equal to 0, f is equal to 0, so this term disappears, is equal to 0. And what remains is integral 0 to 1 minus integral from 0 to 1 f of t kx prime double prime t dt. True. And but even if k is not two-wise continuously differentiable, we can give a meaning to this using the theory of distribution. The identity f of x is equal to integral from 0 to 1 f t k x double prime t dt with minus is also valid for functions which are infinitely differentiable with support inside the open interval 0, 1. That's the theory of distribution. So we do not want to go into detail of this, but at least we can assure that this is true whenever f is in C infinity of 0, 1 and of compact support. And moreover, this restriction is also important. Support of f is inside the open interval 0, 1. It doesn't touch the boundaries. And we can do this. We can do pretty much what we call integration by parts. But now we look at this as a distribution. So this is the derivative of this as a distribution. And for this, now we have f of x equal to, on one hand, integral from 0 to 1, f of t kx double prime t dt. And at the same time, we know that this is also given by the Dirac delta measure anchored at point x. So we can also write this as 0 to 1 f of t d delta x at t. Delta x is the measure that. Attention, the way I write here is the way mathematician write. I write d of the measure. In some engineering books, instead of this, they write delta x of t dt. So you need to be careful which text you are looking for. And so if we compare this, we see that k has to satisfy this identity, which is a differential equation in the sense of distribution theory. And now we want to solve this. How to solve this? I just borrowed this fact from distribution theory again, which is not difficult to prove. Even I can leave it as an exercise to prove. Consider the function u defined this way: for t positive equal to 1, for t negative equal to 0, and for precisely at point t equal to 0, it really doesn't matter. You can define it the way you like it. So u of t is defined for t positive 1, for t negative 0, and for example, to have it right continuous, I put identity here. It is called a Heaviside step function. It's a very important signal in engineering, in electrical engineering. So Heaviside. Function. And with the interpretation I gave above, the exercise is this. Show that u prime with respect to t. If we forget the distribution theory and we consider what we have studied in analysis 1 or 2, our answer would be u prime is equal to 0 for t is strictly positive, and also for t is strictly negative, and u prime at the point 0 does not exist. That's a perfectly correct answer if we stay in the context of classical derivative. But with respect to the one that we consider for distribution, this is equal to dt and delta t, and delta t is the same as delta 0t, the one anchored at the point 0. If you look at, for example, any book on circuit analysis in electrical engineering, they really define delta to be a function, not a measure or a distribution. And the way they defined it, they say that it's a function which is equal to 0 everywhere. And at the point 0, it's equal to infinity. So that's the way they define delta t. And then ask, how do we use this function? They say the way to use it is by this formula: integral of f of t delta t dt is equal to f of 0. And with this, it works very well. They solve many interesting questions in circuit theory. And also from historical point of view, it is interesting to know that way before Laurent Schwartz introduced distribution theory, it existed among, for example, people in physics or other sciences, and they used it with naming generalized functions. So functions like this. And then Laurent Schwartz, I mean, tried to and succeeded to give a mathematical basis to this. And nowadays, us, instead of writing delta t dt and treat it as a function, we write it d of delta t and we treat it as a measure or distribution, and everything has a very solid foundation. So that's as a comment. So just show that u prime is equal to delta, and if you shift it by x, ux is defined the same as u, is u of t minus x, so it's the same step function, but this jump is at the point x. And oh, what's happened? I'm sorry, I don't know why my crayon stopped. Technical problem. Oh, really doesn't want to work. My apologies. Oof. Please give me a couple of minutes. I go downstairs to see if the technician can help me. My apologies. I stopped the recording now. Where is the recording? Pause.
Thank you. And I go here. Should plug my computer. See, one virus has changed our life. Even our teaching is different. Okay, we are good now. So, are we good to continue?
Yes.
Okay, thank you. So we were here. We are right at the point that we wanted to solve this differential equation k double prime x is equal to minus delta x. And to do this, I define the function u, or the shifted version ux, with the property that we know u prime is equal to delta x. So this is the tool that we use or borrow from distribution theory for not going into detail. There are some ways, for example, Laplace transform, other methods that we can use and solve this equation. But with this, we have a shortcut and we can easily find the solution. So now we see that kx double prime is equal to minus ux prime. So take the antiderivative of both sides once. It's kx prime is equal to minus ux plus a constant. And note that the constant is with respect to t. because the operations are with respect to t. And so c can be a function of x, and indeed we will see that it depends on x, but c doesn't depend on t. C does not depend on t, but it may depend on x. And there is another difference here. From now on, even though kx prime is equal to minus ux plus a constant, is again another ordinary differential equation for distributions, but we can treat them as the differential equation that we know from now on, from the first derivative. Kx prime is a well-defined function, ux is a well-defined function, so is a regular ODE. But both interpretations end up to the same thing. And we need to do one more antiderivative to find the answer. But to do so, recall the definition of ux. The definition is like this: is equal to 1 with minus in front is minus 1 plus c if t is bigger than x. If t is less than x, u is 0, so it's just c. And so when you do the antiderivative one more time, kx of t becomes ct. It's better to write c minus 1t. C minus 1t plus another constant, which I called it in my note E. This is for t bigger than x. And for t less than x is just a constant, which becomes c times t plus another one, which I wrote d. Again, c, d, and e are constant with respect to t, but they can depend on x. So what do we have here? We have a function kx. When we look at the graph of k, from 0 to x and from x to 1, we see in both cases there are lines, a line like this, but and like a line like that. And now remember that we want to solve it such that at the end of the day, k of x needs to be in h. So there are some properties or conditions to be respected. And for sure, k has to be continuous. So one important property that we need to observe is that k of x is continuous at the point t equal to x. In other words, we need to have something like this. And this is equivalent to say that kx as at the point x plus is equal to kx at the point x minus, according to these definitions. Therefore, oh, too much. What's happened? Therefore, if you put t for t times to x from x bigger than x and t times to x from t less than x, we see that this is equivalent to c minus 1x plus e is equal to cx plus d. So cx with cx simplifies, so minus x plus e is equal to d. So it's a relation between two constants, e and d, and at the same time you see that these constants have to depend on x. So we can get rid of one of them here. Either write e in terms of d or d in terms of e, and this gives us this formula which I need later on, kx point t is equal to, now despite that here I wrote a strictly less than x and a strictly bigger than x, now I can write this formula is equal to ct plus d if t is less than or equal to x, and then c minus 1t plus x plus d if t bigger than or equal to x. In both cases, I can put x. Now I have a function like this, which at the point t equal to x is well-defined, is continuous. And now we have to respect other condition. In this case, in these examples, we also want that kx at the point 0 to be equal to 0 and kx at the point 1 to be 0, because it has to be in the space H. And now we put in the equation here, and we find our c and d. Kx at the point 0 is this one, is for t less than or equal to x, is simply equal to d, and this has to be 0. And kx at the point 1 is c minus 1 times 1 plus x plus d. This one also want to be equal to 0. So this implies c minus 1 plus x is equal to 0. So c is 1 minus x, which is okay. C just doesn't depend on t. So we see that our k is obtained is equal to 1 minus x equal times t. This is for t less than or equal to x, because it's simply c times t, and d is equal to 0. C is 1 minus x times t, and for t bigger than or equal to x is d is 0, c minus 1 is minus x, so it's minus xt plus x, which I write it as 1 minus t times x. So that's the formula we obtained for x. And now you see that the advantage of this. This is also is equal to k of t and x, if you wish, the formula for capital X. You remember? Yeah, there is a question.
Is it 1 minus xt or 1 minus xx?
I go here. Yeah, is c for this case is c minus 1. C minus 1 is minus x, so it's minus x times t plus x plus d, which is 0. True. And when I factorize x, it becomes 1 minus t times x, which I wrote here.
Yes, it's
True. Okay. And the same for the other one. And now a very important formula, which I will use several times. I mentioned before, I mean, this technical problem happened. Norm of x as a functional from h to r is equal to is equal to norm of kx, which is equal to kx at the point x root of this, or root of k capital X, x and x. So any of this you can use here and see immediately that in our case, norm of the evaluation functional as a functional from H to R is equal to root square. Evaluate this at point X is 1 minus X times X. That's the precise value for the norm. And recall that with estimation. So recall that we had estimations that the norm of X is bounded by one of them less than root X and by another one root of 1 minus X. And none of them, you see that now is optimal. The optimal one is this one, which is the best and shows the power of RKHS. I see, let me see what is in the chat. Okay, no, it's not a question. So, yes.
While you had got a formula for kx of t where there were 3 constants, C, E, D.
Yes.
And you only use 2 properties, kx being continuous and the boundary condition to
Yes.
evaluate C, E, and D, right? But
Yes.
kx being is in H, then there are many more conditions it satisfies. It should be absolutely continuous and
it
X
is.
prime being.
It is indeed, because it's something linear. I mean, the kx has a very simple formula. If I go back, yeah, you see, over here and over there, kx is linear. So when you take the derivative is a constant, and constant, 2 different constant in general case. It's okay, it doesn't matter. 2 different constant is in L2. So what were our conditions for being in H? The derivative being in L2, that's one thing, being continuous and is equal to 0 at the endpoints. All of them are satisfied now. Do you agree?
Yeah, maybe.
Yeah, but you're right. The point you raised is a good point. You say that, and it should be considered in other examples we will see. What you say is that we have a differential equation. That's good. We obtained the general solution. That is good too. And now it doesn't mean that automatically what we obtain is a member of the space. We have to satisfy, or I mean, verify the other conditions. That's a good observation indeed. And here, well, I didn't explicitly mention that. You will see in our subsequent examples, the point you raise is very important, because pretty much we will have similar differential equations like we saw before. So the solution will be something like this, but the boundary conditions are different, or the inner product is defined differently, and we need to verify if the properties are satisfied or not. We will see, I mean, momentarily some other examples. Up to here, is it okay for you? Everybody's fine?
Yeah, sir, there is one more question. Once we have got the equation kx prime equal to minus ux plus c, after that it was elementary stuff.
Yeah.
Analysis 1 and analysis 2.
Yes.
But coming to kx prime equal to minus ux plus c, you were basically using some facts from distribution theory and all.
Yes.
Is there some other easy way to say this? Because
yes, in my notes, and even somehow it's mentioned in the book of Vern Paulsen, but in my note I mentioned another second method to find the kernel without using the distribution theory. It works, but in a sense, when you read the notes carefully, on one hand, you see well, it works, it gives us the final solution. But on the other hand, in a sense, we are cheating because we have used other methods to find the kernel. We know what is the kernel, what the kernel is. And then we adjust our strategy to find it. So if I want to answer your question, yes, there is a method, but the ultimate solution, there is no escape. You need to know a little bit of distribution theory to fully understand what's going on.
You have a question in the chat.
I'm wondering whether finding K always reduced to solve a differential equation. Not necessarily. In the examples I started, and I will continue today, we have differential equations. But then when we enter our second category of examples, analytic function spaces on the open unit disk, we will see H2, the Hardy space, Dirichlet space, Bergman space, and even Dobranj-Rovniak spaces. In those cases, there is no differential equation. We have Taylor series expansion, and based on Taylor series expansion, we find the kernel. So no, not always a differential equation. Okay, thank you indeed. So before going for the second example, I would like to highlight this, that kxt given by this formula, that's the general solution of this equation that we saw above. It should be, the equation should be a bit up there. K, here it is. That's the general solution of this. I emphasize on the general solution because in next example, we have again this differential equation. And so I do not repeat everything which is written here. I just apply it to find K and then the norm of the evaluation. So, okay, this said, Sobolev space 2, so let me call it example 2, is like the previous one. H is the space of function defined on the interval 0, 1 with values in R, such that F is absolutely continuous. And we also add that F prime being in L2. And now I add just one boundary condition, F of 0 equal to 0. And immediately you see that there should be some problem. I mean, as one of you a few minutes ago mentioned, we verified the boundary values F of 0 equal to 0. We found one constant, and F of 1 equal to 0, we obtained another constant. And here we just have one condition, F of 0 equal to 0. So if we end up with a differential equation of degree 2, how do we find the other constant? So that's why the question yes is very relevant here. The inner product in this case is the same as before. We can define integral from 0 to 1 f prime t G prime T dt, exactly as in the previous case. And it's a genuine inner product. This condition is enough. The only thing which, I mean, might be suspicious is that if the norm of f is equal to 0, can we conclude that f is identically 0? This is really the case, because if norm is equal to 0, then integral from 0 to 1 f prime squared is equal to 0. And this implies that f prime is equal to 0. Be careful here, not for all point, almost everywhere. But absolute continuity is relevant here. We know that f of x is given by f of 0 plus integral from 0 to x f prime t dt. This is not valid for all functions. It's just for absolutely continuous function. And indeed, we adopted this as a definition. And now condition f of 0 equal to 0 gives us 0 plus 0 is identically 0 for all x. And we are done. So this, even though it's just one condition, it's enough for us to give us a reproducing kernel Hilbert spaces. The verification of other things and the fact that the evaluation is continuous is precisely as before, with one exception. In this case, we just have this representation, this one. It means that f of x is equal to integral from 0 to x f prime t dt. And if we do Cauchy-Schwarz, f of x less than or equal is by Cauchy-Schwarz, integral from 0 to x 1 squared dt root square times integral from 0 to x f prime t square dt root square. And the first one gives us root x, the second gives us, I mean, integral from 0 to 1, be generous, right? Integral from 0 to 1 instead of 0 to x, the same thing. And we obtain root x norm of f in H. So evaluations are bounded and we have just one. Estimation for the norm. But is this optimal? We do not know. We need to find the norm, and you know how to do it. To answer this question, we need to find k of x. And the procedure is the same as before. We have a differential equation to be satisfied. Let me see. So if we start with this and we do integration by parts, we obtain precisely as in the previous case, minus integral from 0 to, let me do the calculation. F of x is f inner product with kx in H. So it's equal to from integral from 0 to 1 f of x prime k of x prime dt, as in, I mean, nothing is different. And if we do integration by part, what do we obtain?
there will be extra term f1 of kx prime 1 minus integral 0 to 1 ft
Yes,
kx
indeed.
double prime.
And let me assure you, you obtain the same thing, because when I write f of t, kx prime t, t from 0 to t to the 1, minus 0 to 1, t dt. Do you see why still I write here 0? That's the point I wanted to highlight. Still, even though my condition here is this one, boundary condition, but when we want to obtain the differential equation, still I write 0. It seems there is a problem, because this is equal to f of 1 kx prime at point 1 minus f of 0 kx prime at point 0 minus the rest. You might use the boundary condition and say that this is equal to 0, but there is no clue that this one has to be 0 too. And indeed, it is not. And we will see this is one of the obstacles that we need to remove. Also, at the same time, remember that we are working with the class of test functions, f, to obtain the differential equation. F is in C infinity with compact support of 0, 1, and also the support of F is in the open interval 0, 1. We are working with this class of function, not the whole space H. So if 0 and 1 here, the function we consider are something like this. A little bit bigger than 0, everything is 0 from minus infinity up to here. And also a little bit less than 1, say here, everything is 0. Even if we want to extend to infinity, it's okay. And the action is happening in between. And the function is indeed C infinity. What I need is that at the point 0 and at the point 1, the function is indeed equal to 0. I repeat, not all the function in a space H. No. The subclass I consider, which is called the test functions. For them, it's equal to 0. And therefore, we obtain again the representation f of x is equal to minus 0, 1, f of t, kx double prime t dt. And this, considering the Dirac measure that we saw before, it gives us the same differential equation, kx double prime of t equal to minus delta x of t. And once we obtain a general solution of this, it was up here. It was precisely, no, that was up after, it was up here. Once we obtain the general solution of this differential equation of order 2, and being of order 2, it is natural to have two constants. One of them is D, the other is C. And how do we obtain this one? At least we can obtain one of them or a relation between them, because K of X, which obtained by that formula, Should I repeat the formula? No, the formula is up there. So let me, for reference, I repeat the formula so we saw. The general solution. Kx of t is equal to ct plus d for t less than x, and c minus 1t plus x plus d for t bigger than or equal to x. One condition we have, k of x at point 0, we need to be 0. And if we use this formula, we see that k of x at point 0 is equal to d. So d has to be 0. So we have a function now, k of x of t equal to ct is here c minus t plus x for t less than or equal to x, for t bigger than or equal to x. Still there is one constant to be determined. And back to the question you raised, all the time it's a good idea to verify if we are in the space or not. We are in the space indeed, because what were our conditions? K of x be absolutely continuous. This function is continuous. It has, I mean, the drawing is like this. And then another one. So it's continuous, and indeed absolutely continuous, because the derivative here is a constant, here is another constant. The constants are c and c minus 1. That they are different constants, it doesn't matter. If the derivative is in L2, that's okay. So the most important condition is satisfied, and at the point 0 is equal to 0. So for any value of c, this is a member of the space. That's a good sign. But what else do we want? What else do we want? We also want f at the point x to be the inner product of f and kx, inner product in H. And this is equal to integral from 0 to 1. Yes.
Till this calculation, we have only used the test functions.
Yeah.
And kx being in H, whatever
Yeah.
property.
Yes.
But we have not used any other function which is not a test function.
Absolutely, you're right. That is why that is right. That is precisely very good question. Right at the point. That is why I wrote this. I want this identity to be true for any f in H, not just for the test functions. True. That's the very definition of a reproducing kernel. You ask your question at the right place. Why do I write this? This is not automatic. This is not automatic. I want to have this identity for all f in the space. And now let's see what we obtain. Integral from 0 to 1 f prime kx prime, and f prime has I mean, two values depending if we are between 0 and x or between x and 1. So I write this integral from 0 1 plus integral from 0 to x plus integral from x to 1. Between 0 and x, we are here. K is ct, so its derivative is just c. We obtain f prime t c dt. In other case is c minus 1, the derivative, c minus 1 dt. simplify. Again, being absolutely continuous, this integral is f of x minus f of 0. And that integral is f of 1 minus f of x. Simplify. We know that f of 0 is equal to 0, is in the space, which is good. F of x, we have c here and 1 minus c here because of the minus here. So it's just f of x. That's good. We want this. And what else do we have? Plus c minus 1 f of 1. This term stays for a general element of space. So if we want this identity to be true, we should have c minus 1 f of 1 equal to 0 for all f in H. And since there are elements, I mean, I write in parentheses here, there are f, it's very easy to construct. For example, f of t equal to t in H, such that f of 1 is not equal to 0. E.g., f of t equal to t. So therefore, this implies that c has to be equal to 1. And being equal to 1, you see what is your k of x. The formula is just there. Therefore, k of x is equal to t. If t is less than or equal to x and bigger than x is equal to x, is a constant. C is equal to 1, so it's just x is a constant. So that's the formula we obtain for little k. And now Ex, the norm of evaluation as an operator from H to R is root of kx at the point x, which is root of x. So incidentally, what the estimation we obtained before is optimal, but there was no proof at that point. Now we have the proof. So it is optimal and we are done. Is that okay? So this is our second example. We take a little break and then I have two more examples interesting of the same type. About it's 15:22. We come back at 8 minutes from now.